Hello, and welcome to this lesson on estimating the population mean with sigma known. In this lesson, we will have an introduction, we will discuss point estimators, we will discuss interval estimates, and we'll conclude with confidence interval for the population mean with sigma known. Let's start with an introduction. Using properly drawn sample data to draw conclusions about a population is called statistical inference. The importance of the statistical measures to a decision-making process depends on the confidence the decision maker has in the accuracy of the estimated values. How accurately does a sample mean approximate a population mean? How confident can we be in the approximation? All forms of statistical inference are tarnished with a degree of uncertainty. If samples are selected randomly, the uncertainty is measurable. This allows us to have a level of confidence associated with an estimate. Let's start with some definitions. An estimator is a strategy or rule that is used to estimate a population parameter. If the strategy or rule is applied to a specific set of data, the result is called an estimate. A point estimator is an estimator that uses a single point or single value to estimate a population parameter. An interval estimate is an interval with an upper and lower boundary that hopefully contains the population parameter of interest. The sample mean, x bar, is an estimator of the population mean, mu. A specific sample mean, such as x bar equals 103.4, is a point estimate of the population mean. The following table has some common point estimators and parameters that are being estimated and an example of a point estimate. In the first row, we have a point estimator x bar. The parameter that's being estimated would be mu, and an example of a point estimate would be x bar equals 103.4. The second example we have is p hat is a point estimator. The parameter that's being estimated is p, and a specific example of a point estimate would be something like p hat equals 0.37. And then finally, our last example is a point estimator s. The parameter being estimated is sigma, and a particular example of a point estimate would be s equals 6.4. Good estimators are close to their parameters. How can we judge how close an estimate is to the parameter without even knowing the parameter? That leads us to a definition. An estimator's average squared distance from the true parameter is referred to as its mean squared error, or MSE. The mean squared error for the sample mean is given by the MSE of x bar equals the expected value of the square of x bar minus mu. Ideally, we would have a mean squared error of 0, but there is no such thing as a perfect estimator. Estimators depend on data from a sample that is randomly drawn. Estimators are random variables, and estimates will seldom be equal to the population parameter. Recall that x bar is an unbiased estimator of mu because the expected value of x bar is equal to mu. Of all unbiased estimators of mu, the sample mean has the smallest mean squared error. Now let's talk about interval estimates. Interval estimates are constructed to provide additional information about the precision of the estimate. We will have an interval with a lower and upper boundary that hopefully contains the value of mu. The interval will have an attached level of confidence. The narrower the width of the interval for a given level of confidence, the better. The foundation for a good interval estimator is the central limit theorem, which told us that for reasonably large sample sizes, that would be n greater than or equal to 30, x bar has an approximately normal distribution with mean mu and standard deviation sigma over the square root of n. Since the probability that the standard normal z is greater than negative 1.96 and less than 1.96 is equal to 0.95, and the z transformation given by z equals x bar minus mu all over sigma sub x bar, we can use substitution and algebra to attain the following probability statement. The probability that mu is greater than x bar minus 1.96 times sigma sub x bar and less than x bar plus 1.96 times sigma x bar is equal to 0.95. This means that the probability that a sample mean will be within 1.96 standard deviations of the population mean before a particular sample is selected is 95%. We can visualize that probability by looking at the sampling distribution of X bar. That would be a bell-shaped curve centered at mu. The probability that X bar falls within 1.96 standard deviations of the mean is 95%. This is visualized by looking at the area under the normal curve from mu minus 1.96 standard deviations to mu plus 1.96 standard deviations, and that probability is that area under the curve on that interval, which is equal to 0.95. The provision before a particular sample is selected is important. After the sample is selected, the sample mean is no longer a random variable. So suppose a sample of n equals 100 has been drawn from a population with standard deviation sigma equals 200, and the researcher calculated a sample mean of X bar equals 150. Then sigma sub X bar would be 200 over the square root of 100, which is equal to 20. And our interval estimate would be X bar plus minus 1.96 times sigma sub X bar, which is equal to 150 plus minus 1.96 times 20. This is the interval from approximately 111 to 189. Now, once we have the interval estimate, there's some natural questions to ask. First of all, is the value of the population mean mu inside this interval? The answer to this question is we don't know. We don't know because we don't know what mu is. If someone told me that mu was 100, I would look at that interval and say, no, mu is not in the interval. But if someone told me that mu was equal to 120, I would look at that interval and say, yes, mu is inside that interval. But since we don't know what mu actually is, we don't know if mu is inside that interval or not. Second natural question, is the probability that mu is greater than 111 and less than 189 equal to 0.95? No. That's because mu is not random. It's simply unknown. What we can say, though, is that the interval was constructed with 95% confidence. So we can't be certain that mu is in that interval. We can't attach a probability that mu is in that interval, but we can say that we think that mu is in that interval with 95% confidence. A confidence interval is an interval estimate for a population parameter that is associated with a certain confidence level or confidence coefficient. If all possible samples of a given size are taken from a population, 95% of the samples would produce an interval that captured the true population mean, and 5% would not. In the figure, we have plotted as line segments the confidence intervals from 20 random samples. All but one of those intervals, which would be the interval given by sample number 5, captures the true mean mu. So out of the 20 intervals, 19 of the intervals captured mu, 1 missed. And if you were to construct 100 intervals, we would expect about 95 of them to catch mu and about 5 of them to miss. So the success rate of building the intervals is the 95%. A 100 times 1 minus alpha percent confidence interval for the population mean mu, when the population standard deviation sigma is known, is given by X bar plus minus z sub alpha over 2 times sigma over the square root of n, if either of the following conditions are true. The first condition would be a large enough sample size with n greater than or equal to 30. The second condition would be the data are collected from a normal distribution. So in that case, there is no restriction on the sample size. The term z sub alpha over 2 represents the z value required to obtain an area of alpha over 2 in the right tail under the standard normal curve. So for common values of confidence, we can have common values for the z sub alpha over 2. If your confidence value is 0.80, your z alpha over 2 is 1.28. If your confidence level is 0.90, your z alpha over 2 is 1.645. If your confidence level is 0.95, your z alpha over 2 is 1.96. And if your confidence level is 0.99, then your z alpha over 2 is 2.575. We can also think about the confidence interval as a means of describing the quality of a point estimate. The part of the confidence interval that is added and subtracted to the point estimate x bar is z alpha over 2 times sigma over the square root of n. This can be thought of as the margin of error, also known as the maximum error of estimation, with a specified level of confidence. The margin of error, or maximum error of estimation, often denoted as capital E, is the largest possible distance from the point estimate that a confidence interval will cover. Thank you for joining us.